Good evening, everyone. For those who doesn't know me, I'm Emmanuel David, and I'm Executive Manager here at EPFL Space Center. So as you know, or you don't know yet, but at EPFL, we've been working on the thematics of sustainable space logistics since 2019, and also on space sustainability more in general. And we've been selected earlier last year to be the host and operator of the Space Sustainability Rating. And in this context, also, we are always interested to learn more about what our fellows are doing on space sustainability. And this is why also we invited today Professor Massimiliano Vasile from the University of Strathclyde. He's at the Aerospace Center of Excellence there. And he's going to give us also an overview of the activities on space sustainability that are currently ongoing in his organization. And let's hope that maybe it's for us also the start of further collaboration. That would be very great. And so we're really happy to hear more about what you guys are doing there. So a few housekeeping rules before we start. So you are all muted. And if you have questions, you can either write it in the chat, or at the end of the talk, you can raise your hand and then you will be unmuted so you can ask the question. Currently, the seminar is being recorded. So if you don't want your face to be seen or your name, then I invite you to change it now. So then most probably the video will be on our YouTube channel after. This is, yeah, almost confirmed. So yeah, thank you very much. And then Professor Vasile, I'll let you then start with your presentation.
Thank you very much. I hope you can hear me well. Thank you for inviting me to give this seminar. Good evening, everyone. My name is Massimiliano Vasile. I am the director of the Aerospace Centre of Excellence at the University of Strathclyde. University of Strathclyde is in the city of Glasgow in Scotland. But as you can tell from my accent, I'm not Scottish or British. I'm actually Italian. I got my master's degree and my PhD from Politecnico di Milano. And in fact, I started my career there after spending a few years at ESTEC working in the advanced concept team. In fact, I was probably the first member of the team at that time. Okay, so in this talk, I will give you an overview of what we do in the Aerospace Center first, and I will go very fast. So if you see something that you find interesting, then you can ask me a question about that. And then I will spend a bit more time on the topic of space, safety, and sustainability, which is very relevant for a possible collaboration with EPFL. Okay, let me share my screen. Right, so the Aerospace Center is divided in 3 laboratories. One is the Advanced Space Concept Laboratory. The other is the Future Airspace Transportation Laboratory. And the third one is the Intelligent Computational Engineering Laboratory. And the reason why we structure the center in this way is that we cover research that is easily classified as outer space, and that's the Advanced Space Concept Laboratory. Atmospheric flight, and that is the Future Airspace Transportation Technology Laboratory. And the rest is very much focused on artificial and computational intelligence with many different applications in the other 2 areas, either outer space or atmospheric flight. And you see here at the bottom the major areas of application in which we operate, and one of them is, of course, the space environment, the management of the space environment, and space sustainability. This is a family portrait of the staff in the center. each one has roughly a specialty, but in fact, we work very much as a team. So it's not that we have 3 different silos in which people are confined. I mean, people are floating across different laboratories. We have also a concurrent and collaborative design studio where we do a lot of experimentation with concurrent engineering and system engineering tools, and where we can have also sessions. So if you want to work with us, I mean, we can organize remote sessions, and there we can do end-to-end space mission design and analysis. And we also have access to our own supercomputer, where our computational fluid dynamic people are very happy to keep our technicians very warm. So just to give you an overview of what we do in the different laboratories, the Advanced Space Concept Laboratory, as I said, is very much focused on outer space. We have very strong expertise in orbital mechanics and astrodynamics that goes from designing very fancy trajectories. I worked for ages on Bepi Colombo, for example, designing trajectories for Bepi Colombo, but also looking at uncertainty quantification orbital mechanics, which is a very important topic when then you go into space environment management. We have strong expertise in trajectory design, and that's why you see these fancy trajectories here. The other areas is space safety, and here we cover both the aspect of sensing and detection and tracking of objects in space, and the modeling of the space environment and the long-term propagation of space objects. The other area that is quite important for us is space exploration. Here we have concepts for new missions exploring minor bodies. Minor bodies is probably one of the areas in which we excel. But recently, we also started activities more focused on Mars and human missions to Mars. And then the lab is called Advanced Concept Laboratories because we also look at very futuristic concepts, like, for example, solar power satellite or manipulating asteroids, both deflecting or changing their attitude through different means. And recently we started activities on a new idea, I think, for dealing with space debris, which is recycling and repurposing infrastructures in space. In FAST, as I said, we look instead at what happens to everything that flies in the atmosphere. And we cover both civil aviation, so aerospace and space. So this is one of the projects we are involved in, quite important for us, which is the development of a drone delivery network for the NHS. The NHS is the public healthcare here in the UK. And this is quite an interesting project for us because we are looking at the design and management of the entire network of drones. But we also design or look at the design of future airplanes, future space planes, like in this case, and in general at the analysis and design and control of launch systems. And another thing that we recently started is to look at structural mechanics and in particular the mechanics of joints. And this is very important, and you will see something later when you look at the reentry of spacecraft, because that's an element that is quite important when you try to understand the demise process and destructive reentry and where the fragments are falling. ICELab, which is the Intelligent Computational Engineering Laboratories, as I said, is very much on artificial and computational intelligence. And we cover 3 main areas. One is machine learning and everything that is connected to that, optimization and uncertainty quantification. In uncertainty quantification, we introduce many different techniques to quantify uncertainty, both epistemic and aleatory, into both aerospace and space. And this is a very important thing for us when it comes to trying to determine the position and velocity of an object, for example, when you try to do tracking and orbit determination in space. We use AI also for system design, and we started many years ago to look at what is called resilience engineering. So to design complex systems to be resilient and robust against possible disruptions and failures. And so we have now this interesting approach that turns basically a complex space system into an equivalent complex network. And we use a lot of tools for optimization of the network to then get a system that is optimal with respect to the performance index that we want, but also resilient against possible failures. And then we have these activities on the development of artificial intelligence agents that support the design process. So we are working with ESA on two ideas. One is this design engineering assistant that support the design process through the experience learned from past missions. And we have this chatbot called Scarlet that not only does interact with users in the moment in which they try to design a new mission, but also when it has to collect information from past mission specialists, for example, in ESA, who work on past missions, and they have a lot to say about how to design future missions. So we created this two-way system in which the chatbot can learn from a conversation with a specialist and then can return the same knowledge through a conversation during a design session. Another area that traditionally is very strong for us is a single and multi-objective optimization, optimal control. And that's what we use to design, for example, trajectories. So we have a number of tools that allows us to design complex trajectories for both launch systems, but also trajectories in space, like low thrust trajectories, for example. And one thing that we introduced many years ago was this idea of uncertainty also in the control. We use many different techniques. Some are intrusive, like this one, in which we propagate uncertainty through a polynomial algebra. And some others are non-intrusive, so through, for example, sampling, polynomial chaos, and other type of techniques. And in these areas, together with JPL, a few years ago, we developed this optimal control that we call belief optimal control that integrates both aleatory and epistemic uncertainty when you try to design a mission. And basically what you do, you couple both the optimal control side and the navigation aspects and the uncertainty that comes from navigation into the design process. But we have also intelligence on board. So we are working on projects that are about onboard intelligence for scheduling and planning, and for the control and adaptation of the control of space systems, both in orbit and during the launch. Okay, so that was an overview of what we do, very broad overview. Now, let me go into the specific topic for this talk, which is space sustainability. And my talk will go from what I call space sustainability paradox to a different way of looking at space sustainability, in which we incorporate elements of life cycle assessment into the analysis. So what is I define space sustainability paradox? Okay? Well, here the idea is that, okay, we launch a lot of things into space, and a lot of these things that we launch support our sustainability goals. This is absolutely fantastic. And at the moment, certainly what we are launching into space is helping a lot at achieving these goals. But all the things that we launch into space, of course, increase the problem with space debris, unless we change the approach that we have to launching things into space. And this is probably a figure that you have seen multiple times that give you an idea of the rate of increase of objects that we can track. The objects that we can track are now in the tens of thousands, but I mean, there are probably hundreds of thousands of objects that cannot be easily tracked. And it's not just what is orbiting, it's also what comes down. So the problem is that one of the ways we assume that one of the ways to dispose of debris is through reentry in the atmosphere. But that's not always a good idea. And there is a magic number, which is that everything that re-enters must have a risk of casualties that is less than 10 to the minus 4, so 1 in 10,000. And this is probably a number that makes sense or made sense in the past where there were less objects and less things that were re-entering, okay? But it's probably not the best solution. And in fact, there was a paper that was published very recently this year that was showing that, in fact, there might be a problem in the future if we look at the amount of pollutants that is dispersed in the atmosphere when we re-enter satellite. And at the rate in which we are re-entering now is probably not a massive problem because we have maybe one re-enter every week. But with the increase of the traffic in space, we are increasing the number of objects in space by 1 or 2 orders of magnitude. And if the only disposal option is to re-enter, then we will have an issue with the pollution of the atmosphere. Again, it's not just when we launch something into space or when we re-enter something from space. The problem is also the overall production chain, okay? So is the environmental impact of the entire space sector. Now, because of the limited numbers, this impact is relatively modest at the moment compared to other industries like the automotive industries. But if we increase at the rate in which we are increasing at the moment, then it will become a problem in the future. So the idea here is that we want to take into account this element, these factors already now, rather than going through the same mistakes that happen with other industries and then find that there is a problem. So in summary, what I define as sustainability paradox is that we want to use space, and often space is the best solution that we have to support our ambition to be more sustainable on Earth. And we can provide a lot of very interesting services through the launch of objects in space. But the point is that what has changed in the past probably 10 years is that the private sector has increased the number of launches, increased the number of objects by a lot. And a lot of this increase is only partially regulated. So the dramatic increase in growth of the private sector, is taking us in the wrong direction in a way if we don't use a different approach to the use of space. So what can we do? Well, okay, so the first thing that, of course, everyone is concerned about is space safety and, more in general, what we can call space environment management. And what is space environment management? For me, is a combination of different things. So first of all, we need to know where objects are in space. Okay, so that's the element of space surveillance and tracking. It's not that I want to, spy on people that put things in space, but we need to be able to understand and know where objects are. Simply because if we need to avoid a collision, we need to have information on where the other objects are. And at the moment, Even for collision avoidance, we are talking about very few events, and typically you perform a maneuver, a single maneuver to avoid a single dangerous conjunction event. But going forward, this will become much more complex than this, because there will be multiple subsequent encounters, potentially with the need for multiple maneuvers. So we need also to model this space environment a bit differently from what has been done so far, okay? And introduce elements of automation, what I dare call AI for space traffic management, because it will be difficult to, manage the traffic as we do at the moment. And then there is the topic of disposal, and there is already the need to design things for demise, the D for D. But we have to think of what we are dispersing in the atmosphere. We have to rethink also of the possible casualty risk when things re-enter. And this brings me to the other two topics. One is active debris removal, and the other one is recycling and in-orbit manufacturing, because they are, say, two sides of the same problem. So can we not just design things for being disposed? So it's a bit the same paradigm that we are trying to adopt on Earth, in which we are trying to have a recycling cycle rather than and recycling and reuse cycle, rather than just accumulating trash and throwing it somewhere and parking it somewhere. So one thing that is happening here at Strathclyde and is this Stardust program that in fact started more than 8 years ago, and we were so lucky to have a follow-up grant from the European Commission for what we call Stardust Reloaded. And Stardust is a network of different universities and companies in Europe, but in fact we have partners also outside Europe, in the US and Japan. And we are looking at two things. One is the problem with asteroids and exploration, exploitation, and risk that is involved in asteroids. But the other important element for us is space debris, and especially for Stardust Reloaded, space environment management, resilience, and sustainability. And the interesting thing of Stardust is that it triggered a number of additional collaborations, and we were able to have more projects with ESA, with the UK Space Agency. And so we have now a lot of activities that are all going in the same direction. So one thing that we do in space tracking is this idea of optimizing the number of observations. So if you have multiple stations, typically you want to use them wisely and track the objects so that the uncertainty in the position of the object is minimized. So we propose this strategy to use different resources optimally. And the other thing that we are doing is to develop new sensing capabilities. This is an idea that I proposed back in 2015, and is to use passive radars in orbit. So what is a passive radar? What you see here in this picture, the idea is that you can have any satellite, like telecommunication satellites, that work as an illuminator. So they, of course, emit radio waves. And then what you need is an antenna in low Earth orbit, even a small antenna on a CubeSat that receives this radio wave. And what we look at is the shadow of every object that is crossing the radio wave that comes from any illuminator at high altitude. Okay, so this is a very simple system that doesn't require extra power. It doesn't require dedicated payload. You can have thousands of these antennas and have a very interesting way of mapping the space environment. The other thing that we started recently is this idea of using optical sensing in a different way. So there are a lot of people that now are using light curve analysis to reconstruct the attitude. But we thought, okay, why just looking at the visible range? Why don't we decompose the light, look at an extended frequency range and check the time variation of each individual frequency. So if you do so, and this is a simulation of a cube that has different faces with different materials, what you can reconstruct is the relative abundance of materials on each one of the faces. And you can do it even if you look at the object, and I mean, if the object on the image plane is represented just by 1 pixel, because you are decomposing the light, you're not really looking at the actual shape. So the shape is not really important. And so at least in simulation, we are able to, distinguish what is on the surface of an object in space. We can do this for classification. We can reconstruct the attitude by using, information on which face is pointing towards which direction. And in a way, this is also a way to identify or reconstruct, which kind of behavior an object might have. So I talk about modeling, and one thing that at some point we started asking ourselves is it enough just to know where the objects are and how many objects exist in space, okay, and how many are created during a collision? And in fact, we noticed that if we try to take current models, and you translate this into what is called a multi-layer temporal network, in which you try to understand the relationships among different objects in space. Okay, so for example, you want to understand the relationship between different constellations, or a constellation and a cloud of debris, right? So you understand that most of the models consider the space environment as a lattice in which there are very simple connections and relationship between objects. And this is good if you want just to look at the increase of the density of objects in different orbit shells, okay, around the Earth. But it might not give you a complete picture of what the evolution of the space environment might be. So we started playing with the more complex geometries, with more complex orbits, not just circular orbits, for example, and trying to see how different groups of objects end up interacting. And we are not just concerned about the simple problem of collision. You can have other types of interference. And you have the problem of how much space is actually used by different groups of objects. Okay, so the general occupancy of space in orbit. And of course, this is a problem that is not completely deterministic. So we decide to use a stochastic model for this, in which we define relationships in a probabilistic sense. And of course, the first thing that we did was to introduce a model for the actual collision between different groups of objects to see the increase in the number of fragments, and also the degradation of the performance of intact satellites, okay, the ones that are supposed to be functional. And sorry, connected to this, one thing that we are developing is this Cassandra framework, because once you know where the objects are, once you're able to propagate their trajectory, once you know the risk of a collision, you need to understand how to manage the possible implementation of a collision avoidance maneuver. But that is not the only thing that you can do, because in some cases you don't have enough information to make an informed decision. So it's not that you only need to decide whether to perform a maneuver or not. You might want to schedule more observations. And this brings me back to the idea of optimizing the scheduling of the observation. So we created this Cassandra framework, and one element of Cassandra is to be able to close the loop between observation, decision-making, and the performance of the maneuver. So Cassandra has an intelligent classification system that takes information about space objects in the catalog, including the uncertainty associated to them, and then calculate the probability of collision for a number of potentially dangerous conjunctions. But not just the probability of collision, the added value here is that we calculate also a confidence on that probability of collision. And we don't make a decision only on the pure value of the probability of collision, but also on the confidence that we have in the fact that probability of collision is correct. And through this, we can decide on whether acquire more information through an observation or plan a collision avoidance maneuver. And also the collision avoidance maneuver itself is designed so that we account for uncertainty. So it's robust against what we know and also what we partially know, okay, which is the epistemic uncertainty part that I was mentioning before. Also part of Cassandra is another module that we worked on that is more related to the propagation of uncertainty, because one of the sources, especially in low Earth orbit, is atmospheric drag. And this is dependent, for example, on space weather. So we have a module that is forecasting possible variations in the index that you use in atmospheric models to predict the density of the atmosphere. But we also develop a system that would allow online updating and forecasting of the density, because it's using measurements of the actual trajectory of a satellite in low Earth orbit to then update the dynamic model, okay? So it updates the physical model that allows you to do propagation forward in time. And another thing that I mentioned before is connected very much to what the future Aerospace Transport Technology Laboratory is good at, and is the aspect of modeling the reentry. And as I said, the magic number of 10 to the minus 4 is something that needs to be verified when there is a reentry. So we need to understand exactly how objects are demising and where the fragments are falling if they are hitting the ground. So we developed this tool that is called Titan. The previous name of this tool was Fostrad, if any of you ever attended one of our presentations. But now it's called Titan because we added to the previous capabilities also a multi-fidelity manager that is able to switch between high fidelity fluid dynamic simulations to low fidelity analysis of the reentry. And very importantly, we added structural mechanic analysis that allows us to understand where and when the junctions between different components of an object detach, break, and so initiate the demise process. So we can do very interesting things. We can, of course, analyze objects that reenter in one piece, but we can also look at how pieces are falling apart and falling away. And we can have a map, for example, where the objects or the fragments can reach the ground, as you can see here, where we simulated a situation in which some fragments were hitting the British Islands. But we didn't work only on simulation and modeling. We also looked at the problem of active debris removal. We introduced, in fact, this problem back in 2010-11, and we published this first work. And then we look at two different problems. One is the so-called the orbiting traveling salesman problem, in which you attach a deorbiting kit, and you try to attach as many deorbiting kits as possible within a certain period of time. And the other one, instead, you have a spacecraft that is fetching a satellite and deorbiting, fetching, deorbiting, fetching, deorbiting. And we saw which one of the two was providing the best performance in terms of number of objects and size of the servicing module. And recently, we look also at a different way of removing debris, which is through lasers in space. So if you have fragments, of course, you cannot just attach something to the fragments or grab the fragment. So we look at this possibility to have a very small constellation with lasers in orbit, shooting at fragments as they were passing by. And there are two ideas in the literature. One is use light pressure, but we saw that was not enough to do the orbiting. We could only do just-in-time collision avoidance, or ablation. And with ablation, we could actually reduce the lifetime of the fragments by a lot if we are able to target the fragments as they pass by. The other thing is the idea of recycling and orbit manufacturing. I cannot tell you a lot about this. We have two projects that started this year. One is called CORSE and is looking specifically at recycling modular infrastructure, and the other one is a collaboration with ESA and the University of Edinburgh on in-orbit manufacturing. And this brings me to the last point, which is from space safety to space sustainability rating. And as I said, one idea is that we don't pollute only when we put something into space or when something re-enters, but we pollute also during the entire development of a space system. So many years ago, we started working on life cycle sustainability assessment, in which we develop our own data set, our own tool to assess the sustainability and environmental impact of the development of space systems. And one thing that we did was to connect this to our concurrent design facility so that we could do so-called eco-design. So we could introduce elements of sustainability directly in the design of a space system. And this gives us a trade-off between, performance and sustainability. So we have this multi-criteria decision-making tool that is able to trade off between different criteria when we produce the assessment of the performance of the space system. And more recently, we discussed with Emmanuel about how can we introduce this into the idea of this space sustainability rating. And this means that the space sustainability rating is not only accounting for what is in orbit, but is accounting for the entire life cycle of a space system. So from conception to development, launch, what happens in orbit, and then to disposal. And so there are a number of challenges, of course. We just started working on this, but I think it's a very exciting idea, and also a very useful idea because it would change a little bit the paradigm and would probably address that paradox that I was mentioning before. Okay, here there are some references. I will give you the presentation if you want at the end of the talk. So you can go through the references, download them, and if you cannot, you can ask me and I can send you the reference. And that's me. These are the links to the Aerospace Center, my email address if you have questions, and to Stardust Reloaded if you want to know more about what we do. Stardust Reloaded will continue till 2023. And just to let you know, there's going to be a conference at the end of 2022 at ESTEC that will cover a lot of these topics.
Okay, so thank you very much, Massimiliano. So now if people have questions, feel free to write them in the chat or just raise your hand. So I can unmute you if you want to ask. So I see one hand. Jean-Paul.
Okay, there was a question about the space weather estimation based on the orbits. I would assume that you need quite accurate measurement of your orbits to do that, right?
Yeah, so what we simulated is, some measurements of the orbit, and then we use a filter to do orbit determination. And then we use the estimated state to update the dynamic model.
Yeah, and what is the precision, the typical precision you need to have in your orbits? Say you are at LEO, because you have to be at LEO, I guess, anyway. So is it centimeter? Is it meters?
Well, it depends on, I mean, how bad your model is, because what we are trying to do is to improve over the model that you already use for propagating the orbit. So if it is very accurate, I mean, we are talking about probably centimeters.
Yeah.
If it's very bad, then it's probably meters or more.
Okay, but the models, I mean, we know more or less the precision of the model today. So I was wondering, what is the challenges?
The challenges are that in terms of forecast, we know the models, but they're not necessarily, how can I say, it's not necessarily true that you can very well predict the future trajectory of every object. Okay, because you need to have the density, and then that density has a variability. Okay, so that's one element that we are trying to improve. And the other element that, of course, is not in the slide that I presented, but is the actual drag that the object is experiencing.
Right. Okay. Thanks.
I have a question in the chat from Sigmund. Do you think there is a point at which we will no longer have control over space collisions?
Yeah, but because we don't need it, or because we lose control?
I don't know if the question is finishing like this, but maybe Sigmund can, I'll unmute this person.
Hi, because we lose control, sorry.
Or because we lose control?
Yes.
Well, yeah, well, if we lose control, there is, I'm going to say, little collision avoidance that we can do with that object. But we can still, try to predict the conjunction. And of course, the other objects that can maneuver can do something. But it's important to understand the conjunction and the uncertainty connected to the conjunction also when we lose control, because at that point we have a lot of uncertainty connected to the object. And that helps us to predict possible collisions and what happens after.
Okay, perfect. Thanks a lot.
Any other question? Yes, from Joshua Cayetano Edmond. How worried should we be about Kessler syndrome? Is it inevitable given our current usage of space?
Well, that's interesting. So, there are current theories that say that we are already experiencing that the Kessler syndrome is just evolving slowly. Okay, so it's not as spectacular as in some movies. So should we be worried? I would say yes, not because, I mean, you can see a super fast chain reaction, but because we are already experiencing problems related to, fragments and damages due to fragments and so on and so forth. And the other problem I would say is not just the Kessler syndrome in terms of cascade of collisions, but is really the fact that the traffic will increase. And if we don't want to increase the risk of collisions, we will need to do something, okay? Which is, if you will, not simply propagating the environment for 200 years and seeing how many fragments we generate. Is, can we avoid generating these fragments at all?
Okay, thank you. A question from Chloe Carrière.
Thank you very much for your presentation. It was very, very interesting. Just to give you a bit of a background, I'm a student of EPFL and I'm also a science communicator. And so I engage a lot with the public, and I feel like everyone is getting also worried with the space tourism. And I was wondering if you, in your simulation on the impact of the space sector in terms of sustainability for Earth, is there also a simulation on how space tourism has an impact compared to other sectors of the space field?
So we looked into that, and at the moment is not, in my opinion, the most concerning aspect for two reasons. One is that we are talking about often suborbital flights, or anyway low altitude. They are still fairly limited in number. So I think it would become more of a concern if people were trying to spend more time in orbit, and we're going higher up in the altitude, because the real problem again is the traffic that we have in the congested areas where there is a commercial imperative to put stuff.
You have more questions, Chloe? Or?
Yes, thank you. Just want to reply to that. So you think that it's not the number of launches that is important in that aspect, but more the time spent in orbit. So orbital flights would pollute more than suborbital?
Well, the number of launches for space tourism is at the moment fairly small compared to other launches, and unless, say, it becomes very cheap, it's probably going to remain small compared to other launches. So the added pollution due to that is probably going to be small. And also you don't, you have less problem during reentry. Okay? You don't have to demise the capsule with the astronauts inside. And again, because you are not interfering with the protected regions or the congested regions, there is less of a risk for the occupants. Okay.
Okay. Thank you.
I think Jean-Paul has another question.
Yeah, it's about the UV, the laser cleaning, let's say. This is a great idea, but it has lots of challenges. You need to identify your debris you want to get rid of, or at least to ablate. What do you think is the good strategy here?
Well, okay, so let me say that first of all, it was really a question that we wanted to try to answer. So how difficult it is, okay? How in numbers.
Yeah.
Let's try to understand exactly how difficult it is. And it is in fact very difficult. The most difficult thing is that in the simulation, we assume that we could not really track the debris. So the debris is passing by and you're not chasing after the piece of debris. So you're shooting when you can see the debris. And so you have a fairly limited interaction time. And that is the actual challenge. Okay, so to be able to hit something that is flying by very fast. So, of course, it's a simulation, and in the simulation, we were able statistically, okay, over thousands of fragments, because we simulate the cloud with thousands of fragments. Statistically, we were able, over an extended period of time, to deorbit many of them. But it's not a technique that, you know, very easily can clean up completely the orbit shell.
And I guess it's most efficient if you talk to low orbits rather than higher orbits. I mean, relatively.
Yeah, indeed. It's easier for the simple reason that they are at lower altitude. We decided to start from 1,200 kilometers to have a challenging task and to see how effective it was, because if you start very low, it's easy. And also, we wanted to try to understand the advantage of having something in space compared to a laser on ground, which was the other element that was quite important for us.
Sure. Because I guess you need a lot of energy to be pulsed to your system, right?
You do. in fact, you don't. I mean, the size of the spacecraft that we simulated is not bigger than, say, a telecommunication satellite.
Mhm.
Okay, so we are talking about kilowatts, but the range of kilowatts that is typically installed on a telecommunication satellite.
Right. Okay, thank you.
Okay, thanks, Jean-Paul. And thanks, Massimiliano. I think we have 2 more questions, and that will be the last questions. So one question from Nikila Priyadashini. How is the risk of collision with respect to nanosatellites, and how are the predictions?
Okay, so I'm not the one who simulated the impact of nanosats. Some colleagues who are very against this idea because they think that they are very dangerous. So the problem with nanosatellites is that if they are not in low Earth orbit, low Earth orbit, often they don't have enough control authority or maneuverability to, perform all typical collision avoidance maneuver operations. And that is the critical point. Is not the fact that they are dangerous because they're small, let's say, because we can track them fairly well if they're active. If they are at low altitude, they tend to re-enter relatively fast compared to the regulations. Also, the regulations will need to change. Probably the 25 years rule is not good enough if we increase the traffic. If the number of small satellites is increasing in terms of constellations, then that is, of course, a bigger problem. But all this, of course, is exacerbated by the fact that they don't have maneuverability. Okay, so you can't avoid collisions. So we need something on board this small satellite.
Okay, thank you very much. And the last question for today is, what is your opinion on Russia's latest anti-satellite tests, and how do we avoid similar tests in the future?
Well, I don't want to comment on what Russia did. I certainly can say that the consequence, whatever the reason was, are extremely bad, extremely negative. And how to avoid this? Well, it's a very difficult question because there is no police that is avoiding this. I mean, imagine that if we could do this on a highway. I mean, we could explode things while you're driving on a highway.
Yeah. Okay. Interesting end of this talk. Thank you very much, Massimiliano, for this presentation. That was really great, very interesting. And thank you everyone for participating and for your questions. And so this video might be posted on YouTube. We need to check with Massimiliano if everything's okay in the content before publishing. And yeah, and if you're interested, then check out our YouTube channel. And so we'll see you all for the next seminar, which is on Thursday with our guest hero for propulsion systems. And on this note, I'll say good evening to all, and thank you again for connecting. And thank you, Massimiliano.
Thank you again to you for inviting me, and thank you for all the attendees.
Yep. Thank you. So bye.
Bye.